I want to talk today about breaking out of bounds that we sometimes feel with respect to how we measure things. And you'll notice, if you check in your pocket, that there are some tools available nowadays that are quite different than they were even 10 years ago. And however, if you look at the techniques employed for much of the data that we rely on, very few of these techniques were not available 10 years ago. Is that not right? And so today's talk is really not so much what I like to do in my spare time or what I do necessarily in my lab, but I want to just kind of expand the boundaries a little bit of thinking about making measurements. There's a zillion people to thank, and when I say I, that means we. When I say we, that means I didn't have anything to do with it. And so anyway, lots of people. Thank you, Scott, Mark, Danny, if he's on the airplane, and many more. Okay, so I want to promote a radical reconsideration of measurement methods. We're going to do so by looking at one method in more detail, which is the method I was asked to look into. But I'm going to add another little treat in there because of Christina's or Naomi Tagg's question. And then we can talk a little bit more about the implications of these things. So Mark was the guy who caused this problem because when I came by before my sabbatical and I asked him what I was supposed to do, he said, "You're supposed to measure the temperature of a glacier." And it was a big problem. And I said, "How do you do that?" No one knew, really. We looked at a lot of things. And I said, wait. There was this thing about fiber optics. And I thought back that I'd met it, blah, 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 blah. And finally it dawned on me this perhaps could be a technique that would be of interest for the glaciers. The basic idea is you shoot light into a fiber optic at the central frequency shown here. And then there are side bands. And the side bands are a function of the temperature of the glass. The glass. Nothing outside, just the glass. And so if you take the ratio of the side bands, that takes care of the attenuation that happens naturally. And by timing the return of these sideband lights, you can know how far away you were. So I can therefore send a burst of light, get the echo back, look at the relative intensities of the two side bands, and get the temperature where that light originated. So I can now get the temperature down the entire fiber. So this is called a distributed temperature sensor. The cost range, let's say $30,000 to $100,000. The precision, quite remarkable in that you can measure every little space on the order of 0.02 of a degree C if you're really careful. You can go out to about 5 kilometers in this normal systems. There are systems that will go to 30 plus kilometers, actually. The spatial resolution is on the order of 1/4 of a meter. Okay? So let's just do a little math here. If you've got 5 kilometers of data at 1/4 of a meter, you have 20,000 temperature measurements. Okay? So one of the key things we look for when we're looking at transformative measurements is where we can add some zeros. Okay? So if you have a thermometer that's 10% better than another thermometer, you're not going to have any revolutionary observations. If you have a thermometer that adds 3 zeros in terms of how many points you can measure things at, so we're looking at tens of thousands compared to the tens, then that's actually interesting. And when it measures at a very high precision, 100ths of a degree, that's actually interesting. So it specifically gives us the capability of measuring across the scales of interest that we have the greatest unknowns. Once the water is gathered into the Amazon River, who cares? We can, eat water here, water there, it doesn't change much. But at the headwaters, going down to the first, second, third order streams, that's where there's a lot of uncertainty. A lot of patterning we've seen over these weeks. Over these weeks, it feels like weeks, over these days. No, it doesn't really feel like weeks, but over these last few days, think about the scales we've looked at, okay? They were kind of half meter to, on the order of half kilometer scales. Wouldn't it be cool to be able to fill in the spatial data in the subsurface, for example? Okay. First, I'm just going to lay out just a few examples of use of this stuff so you can see what the data looks like. On the right, you'll see me carrying a cable with Nick van de Giesen, and then my 2 kids who who will be featured later. And I think that slave labor is a useful commodity. But anyway, we went to this river, dropped a cable in it, and we decided to look at what would happen at particular locations. At this location, which went from 103 meters from the headwaters down to 113. So we're just looking at a very little spot. And we notice during the day, that's the upper line, it got cooler at that location. And at night, it got warmer. What caused this? Energy. What was the energy from? Groundwater. So the groundwater was at an intermediate temperature, and that would heat the water at night, cool it during the day. Now, we happen to have a flow measurement upstream of this. So what do we have? We have flow, temperature upstream, temperature downstream at 2 different times. Okay. What's the unknowns? The temperature of the groundwater and the flux of the groundwater. So we actually have more equations than unknowns, and so we can actually solve explicitly for the groundwater temperature and groundwater flux. This is really cool. I mean, if you think about it, a lot of us walk around streams and stuff, and you realize that those streams are coming from invisible locations. And so to be able to lay a cable into a stream and not only know where those locations are, but the fluxes is quite nifty. If we want to plot out a few million data points, we can do so. And here we can see each of the groundwater inflow points. This is time, so about 8 days. Here's temperature is in the color bar, and then distance going from 0 to the first 700 meters of this installation. And here are the groundwater inflows. Here it got cooler. Here it got warmer during the day and during the night. Typical, okay? So we can then plot out the flux down the whole stream. We can also start to look at, and you guys, eco-hydrology, we've been very interested in patterning, but we actually have arid lands for which the habitat is really in the stream. And the stream can get very warm, and that can cause problems for our eco-hydrologic systems. In this case, we're looking at salmon habitat in a river in eastern Oregon. It's a beautiful stream, completely devastated by cows. It doesn't make it look that way, but it shouldn't look like this at all. And we have fibers going up and down each bank. It's located here in the eastern part of Oregon. Here's the Pacific Ocean, California, and Washington. Okay, so here's a bunch of data from 3 successive years, 1, 2, 3 years, and 3 successive reaches. And what you see is a lot of times the left bank and the right bank are similar in temperature. Other times there's actually periods of several hundred meters up to the kilometer scale where in this little stream there's not lateral mixing. And so we see the 2 different habitat conditions on left and right bank of the stream. What we were really looking for here were these what are called cold water refugia. That's where a salmon, which is about to bake in the sun, can find a cool spot in the stream to be able to survive. What was unexpected was there weren't any really. There are essentially no cold water refugia in this river, despite the fact that we had to spend about $100 million to develop the cold water refugia. So we had this problem. Lots of money, no opportunity. Well, let's take a look at what was going on with this. So we saw some minor cold water down to 2 degrees cooler, but very few of those. And the deal is that the stratification was minimal, and you could basically just look at the Richardson number and say, hey, wait a minute. Actually, the shear force here is sufficient to mix at those at those high levels of flow and minor temperature differences. You can also look at the Froude number and get a similar result for the impact of the flow at the end of any little divot, and that actually creates enough turbulence to once again mix this whole system. And so what does that tell us? It tells us that these guys had been digging holes in the middle of the river, and this was not a good plan. But actually, if we go around the back of a corner, there are some very low velocity areas where you could hope, and now we can kind of start to design where to put these according to where we see the proper flow conditions to support the thermal stratification which the fish are looking for. So the deal is that being able to do an exhaustive look at an ecosystem sometimes reveals properties that you couldn't really capture by kind of flouncing down the river. Now, another way to get these sort of data, and this is a tool that I haven't seen much used in this conference either, but it's very exciting, is infrared photography. And so you can get this FLIR and TUR data of stream temperature, for instance, or landscape temperature to do evapotranspiration. There's lots of cool things to be said about this photography. One of the things is that you need someone who's a helicopter pilot. Do we have anybody a helicopter pilot in the room? And these guys tend to be extremely expensive, as we heard earlier as well. By the day, more than my annual salary. We have these guys who fly rarely with great fanfare. And we see that what happens when we take a snapshot of the river is, by God, there's cold patches, really serious cold patches. So here we have this nice big, these nice cold places that salmon should be happy. And so we take a look, 2 degrees, bingo. Okay. Now, year after year, these same places are cold. And so, they keep on flying pilots, the extortion goes on, and they keep on getting data. And now we're going to actually do some restoration at these very high opportunity sites. The problem was that I could not understand how this would be. How does a river spontaneously get cold? It just doesn't make sense. So I set my student on this. We set out the cables, and we said, gee, let's look at one of these spots. Now here we are. At night, it's all cold. Fine. And then as the day goes on, what we see is here we are getting into our cold patch. Look at that, a 2-degree drop, just like the FLIR data told us, just at the middle of the day, which is when you really, right when the hottest time. Then the bad news was that actually, later in the afternoon, that cold patch warmed right up and was now the warmest place on this river. Well, how is that? Well, what if we just took a simple advective model and just said, we're just going to throw in ping pong balls and see how those ping pong balls go down the river, and they're just going to hold whatever temperature they started at, they're going to keep. And it turns out that the advective little ping pong ball model of advection of temperature down the river explains all the variability. It was just a deep, wide spot, and so it delayed the transport of morning water down the river. And so it was just a delay. It wasn't, and it's not, it was at a scale that salmon couldn't possibly take advantage of. So again, it was a kind of, you had to be careful, and this is, I think Jeff brought up the notion of orthogonal measurements. And so just taking the FLIR data, we were planning entire restoration efforts based on that data. And actually, it was much more interesting and complicated, in some ways, perhaps even simple. Now, again, getting to the restoration issue, Mark had a lovely stream in Switzerland that he had a bunch of guys go out there and put a cable in, and I was able to steal the data. But not really, I was invited to. But in any case, what I want to make the argument for here is that we actually, what's the utility of a physically based model? Besides just pattern recognition, isn't it nifty to be able to do some prediction? So here's a lovely meandering, well, not, the meanders are very subtle, Swiss stream, and the headwaters are that cylindrical object up there. So there's the headwaters, and then it comes out, and it's exactly 2.35 meters wide. The interesting thing is that midway down the stream, it filled up with reeds. Okay, this is a very bad thing. Farmers don't like these. They clean them out all the time. So that was, but it was an opportunity for us to look, can we explain the effects of reed on the stream? And then you go into the forest. And then you get a bunch of wonderful students from across Europe to help develop the sensor scope platform. And so we put this is a royal use of we. They put sensor scope platforms out here, and they were able to measure the boundary conditions essential to obtain to model this system. So we use a very simple thermodynamic model, a very simple energy balance model, just energy in, energy out, and off we go. The cool thing is, when you've got a really rich data set, you can do really rich verification of the model. And we can verify it not only on one condition, but under reeds, under open, under forest, etc. So now we have a richly validated model, and we can play what if. What if it was all forest? This would be bad for the farmers, because you have to set aside a lot of land, but it's very nice, and it knocks off about 2 degrees off the stream temperature. In this case, the critical stream temperature is 17 degrees, and that's when the local migratory fish that are living otherwise in Lake Geneva have physiologic problems. What if you cut down all the trees and satisfy the farmers, get the reeds out of there? It's now classic, and what you get is dead fish. So it does bounce up the temperature significantly, on the order of 3 degrees. On the other hand, the cool thing about reeds is they're very quickly established, and they don't take up any of the farmer's land. And so, interestingly, if you were to cut down the trees, which I guess the guy who owns the trees might want to do at some point, you can actually maintain acceptable temperatures using reeds alone, which is kind of a nifty finding. So you don't have to sacrifice everything up the stream. Interestingly, downstream is where the fish live. So although there's lots of discussion we could have, but it is actually a feasible strategy. So I guess the point is here that, number one, we have a technology which measures the right things. Number two, we have a confidence in an actual physically based model for which we can make, upon which we can make decisions. One of the, so this fiber optics, there's a lot of different things you can do with it. I'm only going to talk about a couple. But one of the interesting things in an ecosystem is what's the distribution of shade, for instance, and what's the distribution of air temperature under your canopy. So you have this spatially variable canopy, and what if we want to know what the temperature and solar exposure is in there? Well, let's see. So what we want is temperature and exposure to sun. So temperature we know we can get. Exposure to sun, all we need is one more equation. So one more equation can be had by adding another color of fiber. So now we have a black and white fiber. We have two fibers, and we're going to measure the difference in temperature between them, and by that be able to get the solar radiation. And then by using by looking at the white cable alone, we can get the temperature, and then you do some adjustments. But basically, we have two equations, two unknowns. Here's Ari putting it in over a stream, and we get a very nice linear relationship between the cumulative difference in temperature between black and white versus the percent solar radiation that it's exposed to. And what we can do is start to do two-dimensional time and space grids at 25 centimeter resolution of the entire shade and temperature pattern, say, under your canopy. That's pretty nifty. So let's go underground, though. So soil physics guy, and so the holy grail perhaps in soil physics is where's the water? And so wouldn't it be cool to be able to measure the soil water content continuously along a transect, continuously in time? So let's just use a very standard method, the method we've seen actually earlier today, the heat pulse method. So if you put a heat pulse in a cylindrical injector and it's surrounded by thermally conductive media, then the thermal conductivity and the thermal heat capacity of that media is going to dictate the time rate of increase of temperature and the time rate of decay of temperature. So that's all we're going to do. I'm just going to it just turns out these fibers can be bought with metal jackets. So I'm just going to put high voltage on a metal jacket on a long cable, a kilometer long, and I can heat that whole cable up with exactly the same amount of energy per unit length. And then we can see what we can learn. So here we are in the lab. We've wrapped helically this fiber optic down through what's going to be a soil column, put in a bunch of TDR for verification, and dump in a bunch of sand. And this is the type of data you get from a heat pulse experiment. Basically, in dry sand, it heats up more and cools off more slowly. And here in saturated sand, it doesn't get as hot. Using a longer, higher energy pulse, you get cleaner data. Okay, and you can make a calibration curve, and there's a lot to be said about this, but you get the water content versus the cumulative area under that curve. So it's a very simple calibration. Go out to the field, get yourself a caterpillar. I think these are fun. And then here we go. So we have time, distance along a transect. So we put in 3 cables at 30, 60, and 90 centimeters depth. And we're just going down a 200-meter transect in this case, or 250 meters. And you can see at the peak of the heating, you see all that texture? And that's basically, the area under that is proportional to that texture, essentially. And so that's telling us right away that there's some interesting dynamics in the soil. So go let the guy do some irrigation. He's not very, he's got his sprinklers right in the corn. So it's highly spatially heterogeneous, the watering pattern. And this is what you get. So what you have here is looking at the 30 centimeter depth and the 60 centimeter depth. 3 hours before irrigation is the black line. The green line is 3 hours later. The red line is 9 hours later, and then it's 15 hours later. And this is water content. So you can see there were these local isolated points of infiltration, and they were consistent between levels. And so we can actually watch with extremely high spatial resolution the dynamics of soil water at this site. And anyway, that's pretty helpful. Well, and you can get the velocity out of that by doing kind of a mass balance. You can say, okay, here the water content changed this much, it took this long, there must be this flux. But it'd be also nice to get the flux per se. And in this case, we're going to go directly to the sap flow people and say, how do you get the flux out of your sap flow? Well, you put in energy. There's two ways to do it, you know. There's one is the translation of energy, and the other one is just looking at the single probe method. Let's use a single probe method here in a wetland. This was designed to be a leaky wetland, as it turns out. So we put in a bunch of fibers. There's our little trolley. We put in 4 fibers, and the blue one's the one I'm going to heat. And those are some data. So the blue curves are a suite of different data from different points along that cable in time. And what you notice immediately is some of them are higher than others. And that's simply a matter of flux. A higher flux, the more energy that's sapped from the cable, and the greater so the lower the ultimate temperature is. So we simply measure that delta T, put it into this very nice little equation, and we can actually get in space and time, once again, the actual water flux distributed across this site. So, you know, and this is, I guess I would kind of, I don't know about Holy Grail, but it's pretty important stuff from a hydrologic point of view. Just going to check on my time here. I have another 3 minutes and 55 seconds. Okay. I want to just show one other little example. Oh, boy. I'd like to show more examples, but another example that illustrates the density of data you can get. And here we're going to a mine shaft in Nevada, and we want to know what the flux is through the groundwater system. So here's the typical geologic descriptions. There's a lot of texture there, but you know, the geologists are basically waving their hands. So what we do is, I told you we get more slave labor involved. If I can get this thing. So what we do is we take 2 fiber optic cables. Those are the red guys there. And then we take my old skateboard. I'm no longer using it. So we take it apart. And this is and what they're doing is winding this one wire around the others and ending up with this spool of cable. And so what they've done is they've taken fiber optics and they've wrapped heating elements around it at distinct locations, 2 meters on 2 meter separation here. Okay. It was a lot of work. There's roughly 300,000 wraps on this thing. My son's hands fundamentally changed geometry. We pot the end of it in a PVC tube. Then you can do a couple things. The first thing you can do is just not do anything, just take the data, and what you get is the thermal profile, and you can then calculate the thermal conductivity of the rock just by, you know, straight, you know, assume that there's no generation of heat in the middle. Interestingly, we had these guys drilling holes near us. That's like 20 meters away. They were injecting mud, and we were able to tell them exactly what was going on there. But in the bottom line, most of it, we can just calculate the thermal conductivity of this. Having that in hand, now let's put a heat pulse in. So here's the heat pulse, and all that raggedness is my kids' hard work. This is after just at 4 minutes, and this is after 24 hours. That's what it looks like in time. So that comb of data are those heat pulses. Now we're looking at just a very few of them. There's 350 out of it. Okay, so and here we go. We're looking at the heat pulse after 24 hours, after it's decayed a bit. So, and what we see is a lot of interesting stuff. Let's do a blow up here. Here's one typical thing. So what we have is this is the heat pulse when it was injected. Let's see, the red one's when it was injected. The blue one's after it's diffused, I think. So the point is that these things are actually translating up and down. So the heat pulses are translating up and down, and that gives us the local vertical velocity. And then the magnitude of these peaks gives us a local horizontal velocity when corrected for the thermal conductivity. So we can get the full vector flow field, at least you can get the horizontal and vertical components out of this. And in fact, yeah, we do get the direction. So this, I think, from a groundwater hydrology point of view, is fairly important because to this point, we've had people waving their hands around a lot. Okay. This DTS stuff, if you want to learn about it, Scott and I run trainings, and so we'll run one in Luxembourg. I'll run one in Luxembourg this July, and then right before the AGU, we'll run another one, a 2-day version. So you're welcome to come to those. And with that, I think I have just about a minute left. Yeah, half a minute. I wanted to show you guys one other thing. I may not be able to get to it. Well, I'm going to answer Christina's question. So Christina said, is there some cool way to measure the canopy interception? Because you guys are eco-hydrologists. And so what we did is we started by measuring the compression of the trunk. So we measured very carefully the compression of the trunk. You may have seen those papers. But the one you haven't seen, and that is coming up, is basically making use of this same technology. It's just about to run out of time. And it has an accelerometer in it. And this, yeah, time's up. It has an accelerometer, and the trees sway in the wind. And the interesting thing about trees swaying in the wind is it's a resonance that's a function of the mass of the stuff in the upper tree. So simply by measuring taking the Fourier analysis of the frequency that you see in the naturally resonating tree, you can, with a calibration weight, you can thereby watch the dynamics of sap accumulation, loss of water in the tree, the weight of the leaves that were put onto the tree. You can see all sorts of amazing things about the mass dynamics of the tree. And a data logging 24-bit accelerometers now are on the order of $90. So with 2 gigabytes of data. So you can get 300 hertz data if you want it. But point is to your heart's content. I guess to sum up then, I know it's just a slight bit over my 25 minutes, but don't think within the box on instrumentation. Face us with what you really want. Be it a glacier or be it a canopy interception, face people with what you want, assume it can be done, and then put in the hard work, and we can get these measurements. Thanks.
Thank you. First question, maybe.
Yeah.
What's the cost of the system?
Of a DTS?
Yeah.
Yeah, that was you can get between $10,000 and $100,000 for the instrument, and between $1 and $10 a meter for the fibers.
Okay. Thank you. So questions,
Jeff?
Please.
John, this is so exciting. I think in hydrology, the holy grail measurement is stream flow. We've just come off of a decade of prediction ungauged basins. Why? Because most basins are ungauged. Is there any way with the fiber optic or other things you've been thinking about to get distributed flow along the length of a stream? Just think about how that would transform our ability to interrogate models or understand systems. Is there anything you could do with heating the wire in the stream somehow to measure discharge directly? I think that would be a game changer.
I think so. And let me just, this is thinking on the fly. But there's this, I didn't mention it otherwise, but there's one that measures, we can measure with fiber optics temperature, but also actually sound. I can measure the sound at every point along that cable at 100 kilohertz. What can we do with that? Well, the interesting thing is you get the advective velocity because you get a Doppler shift of the sound going down the cable and going up, and you get the depth of water because there's a resonance of in the vertical water column. So in fact, we just went and plunked an acoustic cable in a river, and I hope I'm able to give you more than just a big hope on that, but I think we should be able to do that. Let's get some non-Oregonians. No, I'm sorry, Gordon. I'm sorry.
That was just a quick follow-up. You could also get bed load.
Yes. Oh, yes. No, that's what we're doing. We sat there throwing rocks around in the river quite a bit. Yeah. Oh, yeah. Go ahead, Ronnie.
Are there limits really in terms of are there limits in the media that you have to observe? Does it need to be in water or ice? Can it be in air or something?
Oh, great question. Oh my gosh. So, I mean, if you actually look in EOS, you'll see that we published a paper in air, but the most recent stuff we just finished up in Colorado, we did the same heat method, but in the air. And so we stretched it across a whole valley, and it just turns out the wind would come over the top of that valley, and there's this little kind of cornice of air coming over, I call it, because I'm a skier. But basically, we could watch the tumbling air going across our fibers. We had 3 fibers at different elevations, and get 1-second resolution of the air velocity and the air temperature. And so you can use both of those to learn quite a bit about the air movement. Yeah. And then I think Mark's group sent a balloon up, and you can use it as a vertical sounding as well. And we've done that as well.
There is a question.
Yeah.
Yes.
Oh. Hello?
When you measure the soil water and the infiltration, do you need to know the soil texture or soil hydraulic properties to get the calculation?
That was not a planted question. Yes, and calibration is obviously challenging. So that's what we're working on right now, and Chadi is literally in Oklahoma poking thousands and thousands of holes with his thermal probe to get those properties. But yes, we're working hard on how universal we can make the calibration. Can we do it by observing under known conditions, for instance, really dry and very wet, and use those as interpolation points? But yes, the calibration is a wide open challenge. Very interesting question. Yeah.
Joe, a word about the signal analysis that you do at the very end of the fiber. What do you need to do in order to get the temperature?
The signal analysis to get the
It's not only the fiber. What the instruments does, except for the fiber itself.
And they keep, if you believed what came out of the box, then I have a bridge to sell you. And so no, what you do is you very carefully calibrate the instrument. So we run the light out on a fiber, we turn it around, run it back, and at this end, where it comes in and out, we have it go through two different baths. One of them is a slush of ice, so it's at 0. And the other one has a mixer and is at some measured temperature. And so basically we've got the temperature constrained high and low at both ends of the fiber. And that's the only way you can get really accurate measurements. Is that what you mean?
Okay, I think we'll have to.
Okay.
And thank you very much.
And thanks for your patience. I was slightly over the top just because I knew it was right after lunch. So I appreciate your forbearance.
Thank you.